So we're going to talk about scatter plots, association, and correlation. So we talk about the normal distribution and standard deviation and stuff like that. But today we're going to focus on scatter plots. So scatter plots may be the most common and most effective display for data. In fact, if you look on all of my posters of all of my research, there's some sort of scatter plot of some form or fashion. So it's used a lot in scientific research and business, any type of modeling that needs to be done. Scatter plots are the best way to start observing a relationship and an ideal way to picture associations between two quantitative variables. Now, we're going to use very careful language on this. We can't say that one thing causes another. We can only see that there is an association between two parameters, right? There's a parameter between, or there's an association between someone's height and their weight. If somebody's taller, they might weigh more. Does that make sense? All right, so when looking at scatter plots, we'll look for direction, form, strength, unusual features. So let's start with the direction. A pattern that runs from the upper left to the lower right is said to have had a negative direction, and a trend that is running the other way has a positive direction. So this is some real data from the National Weather Service thing. I forget what that acronym stands for. But this is a negative direction because it looks kind of like a line that's going down, right? Think of the slope. If this was a linear equation, it would have a negative slope, okay? It's not quite a straight line, though, but it kind of looks like one. So here's another example of a negative association. It kind of looks like a line, but maybe not, okay? And if we think about it, if there is a straight line, where would you put that straight line? Because that's what we're going to try to do. Is in the real world, we look at data and we make models or write equations that help us to make predictions. So in this particular case, we're looking at the relationship between wind speed and central pressure. And it seems as if the central pressure increases, then the wind speed decreases, right? Well, how much? Can I predict that pattern? Well, maybe. How accurate will those predictions be? Well, that's where statistics comes in. Now, if the relationship isn't straight and it curves, in other words, it's still increasing or decreasing steadily, we'll talk more about that in Chapter 9, but there's other type of models, right? We don't always have to have a straight line. We could use an equation that is, in this case, this might be quadratic, it might be exponential. So we're going to try to find some sort of equation that when I graph it looks like the pattern of the scatter plot. This looks like what? What does that look like? It looks like a quadratic flipped upside down, doesn't it? So, anyways, if relationship curves sharply, the linear method won't work, right? If I write an equation of a line, the dots are going to be too far away from the line. But if I write an equation that's a quadratic that fits through the middle of the dots, that information might be more useful. Today, we're only focusing on straight lines, linear relationships. At one extreme, the points appear to follow a single stream, whether straight, curved, or bending all over the place. On the other extreme, and this is what they're saying, sometimes you'll see something very tight knit. That looks like a line. This does not. This is all over the place. It's impossible to make a prediction about this, okay? I like the fact that they said it looks like a vague cloud, but there's not a whole lot I can do with this data with regards to making predictions. So what we want to do when we look for unusual features, this is unusual. Look for the unexpected. Often the most interesting thing to see in the scatter plot is the thing you never thought to look for. One example could be a surprise outlier that's kind of way off the beaten path. Another thing that's interesting is groups or clusters. So you can have different patterns and different locations. If you look at my research, the poster on thermal rectifiers, there is a linear trend for the thermal conductivity of an object when it is a solid, and then it dips way down, and when the thermal conductivity completely changes when it's a liquid. And that was the whole point of the research. So there's two clusters of information. I had to do two linear models there. Roles for variables. Basically, it is important to determine which of the two quantitative variables goes on the x-axis and which one goes on the y-axis. That might change the pattern. Again, the simple rules are going to be, in algebra we tell you the independent variable and the dependent variable. You kind of keep that same concept, except we're using a little bit different terminology. Y is usually referred to as the dependent variable because the value for y depends on the value for x. So when you set this up, the roles can be clear. The predictor variable goes on the x-axis. What do you think makes the prediction about something else, right? Does weight predict height, or does height predict weight? I would say that height predicts your weight. So that I would put height on the x-axis because I'm trying to figure out if somebody's taller, would they weigh more? Now you could say if somebody weighs more, are they taller? And flip-flop it. But common sense would lean towards the other way. So the predictor value goes on the x-axis, the response variable goes on the y-axis. The roles that we choose for the variables are more about how we think about them rather than about the variables themselves, the parameters that we're measuring, right? Just placing a variable on the x-axis doesn't necessarily mean that it explains or predicts anything. The variable on the y-axis may not respond to any of it anyways. So what our goal is to collect data and see if there's some sort of connection or association between two parameters, right? Height, weight, age, income, right? Stuff like that. When you're younger, you probably got to work a part-time job. When you're older, after you graduate from high school or college, you make a little more money. You stay on the job for a long time. Maybe that might change. Right? So when we collect the data, this is data from students in a statistics class. It included their height and weight. Oh, isn't that ironic? I did not read this ahead of time. Here we see a positive association in a fairly straight line form through what seems to be a high outlier. So they said height probably predicts the weight. And then we have one kid, 72 inches. What's that, 6 feet tall? Yeah. We have one kid that's weighs a little bit more. How strong is the association between the height and weight in the statistics students? If I had to put a number on the strength, we would not want to depend on the units we used. Okay? So they measured height in centimeters and weight in kilograms. It probably wouldn't change the pattern of behavior. So on the first one, they did the height in inches and the weight in pounds. Then they switched it. So the number, like the scatter plot, doesn't change much. So since the units don't matter, why not remove them all together? We could standardize the variables and write coordinates as zx and zy. And here the scatter plot is standardized weights and standardized heights. Note that the underlying linear pattern seems steeper in the standardized plot than in the original scatter plot. So when you standardize it, it changes it a little bit. That's because we made the scales of the axis the same. Equal scaling gives a neutral way of drawing the scatter plot and a fairer impression of the strength of the association. Some points in green strengthen the impression of the positive association between height and weight. Other points in red, they weaken the positive association. Points with z-scores of 0 are in blue and don't vote either way. The correlation coefficient in this particular case is R. This gives us a numerical measurement of the strength of the relationship. Now, I had one professor say, think of it as like the percentage of dots that are on the line. That's not actually true, but it's a good way to think of it. 1 would mean 100%. That's a very strong correlation. 0.9 would be a pretty good correlation, but it's not as strong as 1. So think of it as like a percentage, and that's very helpful. The correlation is 0.644. Well, it's a moderate strength. The closer we get to 1 or negative 1, if it's a negative correlation, the closer we get to 1.0, the stronger the association is. 0.6 is moderate. It's not great, but it's not bad. Correlation measures the strength of the linear association between two quantitative variables. Before you use correlation, you must check several conditions: the quantitative variables condition, straight enough condition, and outlier condition. Probably that outlier really threw off that correlation because that dot is really far away. Quantitative variables condition. Correlation applies to only the quantitative variables. Don't apply correlation to categorical data masquerading as quantitative, because we're doing a bunch of math. And you got to make sure that you have quantitative data compared to quantitative data. Check and make sure you know the variables, units, and what they measure, right? Straight enough condition. Correlation measures the strength only if it's a linear association. It could be misleading if the relationship is not linear. If I were to do that linear, there's a process to find the strength of a correlation. If I do that to any shape other than something that looks like a straight line, the math will just be garbage. Your correlation will be like 0.2 or 0.3 or 0.1. So it doesn't help you at all. Our end goal is to write a linear equation with a strong correlation that helps us make predictions about patterns of behavior. So we only calculate and use the correlation coefficient for linear data. Okay. Outliers can distort the correlation dramatically. An outlier can make the otherwise small correlation hide a large or look big or hide a large correlation. So in other words, that one outlier, again, just like before when we were doing normal distributions, you can make the calculations with the outlier and without the outlier. Okay. There are anomalies that exist in nature. Okay. So remember that you want to get as close to either -1 or +1. The negative is really just, when it comes to correlations, a -1 just means it's a negative slope. All right? It's a negative correlation, but you want it to be as close to 1 as possible. If you get -0.9, that's pretty good. Correlation treats x and y symmetrically. Correlation of x and y is the same as the correlation of y with x. That's actually calculated using a form of the Pythagorean theorem that calculates the distance between the dot and the line. Maybe we'll go over that in some of the homework problems. Correlation has no units. It's literally measuring the distance and averaging the dot from the line and measuring the distance and averaging it. Correlation depends on z-scores, and they are unaffected by changes of center or scale. So remember that when we do the z-score of something, we're standardizing something. Z-scores measure the distance from the center. Really simplifies things, right? So if I measure height, the average height is a certain height. It has a value, it has a number. When I standardize it, I no longer focus on that number, I focus on the distance from that center. Okay? Correlation measures the strength of a linear association between the two variables. Variables can have a strong association but still have small correlation if the association is not linear. We got to look at the scatter plot. If it doesn't look like a line, linear correlations and linear regressions don't help us. Correlation is sensitive to outliers. A single outlying value can make a small correlation large or a large one small. If we look at that one outlier, it really threw off that number. I bet you if we recalculated the height versus weight and we got rid of that one outlier, the correlation would probably go up to 0.8, 0.9. That one outlier can really throw it off. One last thing I want to point is that correlation does not mean causation. The numbers don't lie. Have you ever heard that phrase, the numbers don't lie? The numbers don't lie means that you're just collecting data. There are things in nature that are counterintuitive, right? If I go up on a mountain and I throw a football from the top of the mountain, is that because I'm higher up, is that football going to fall faster or slower than if I'm on the ground? That's the counterintuitive part. It won't. The acceleration due to gravity decreases as you get further away from the center of the earth. A lot of people assume that when I go up higher, but you're further away from the center of the earth, so the attraction between the football and the center of the earth are different as you're further away. Okay. Now, how would I know that? Well, because somebody collected the data. And based on the regressions, and sometimes it's linear. In that particular case, objects in free fall, that's a quadratic thing. But now, does that explain it to me? No, those are just the numbers. Does it cause it? Well, yeah, I guess that's not the greatest example for causation. But we're just looking at the numbers, right? We're just looking at the numbers. Just because somebody's taller doesn't mean they're going to weigh more. Some very tall people are very skinny. Okay? But there is some things, basically, we can only say that the numbers show this or the numbers show that. Right? We can't prove causation. We should never make that claim. Now, some things do cause other things, but when you're doing stats, you can't say this causes that. Right? So, like, I have a headache. I eat chocolate pudding, the headache goes away. Right? Every time I eat chocolate pudding, the headache goes away. Does that mean that chocolate pudding cures headaches? Not necessarily. Now, if I did that a bunch of times, my math would say that there's a correlation. But why do I have the headache? Do I have a migraine headache, or am I just hungry? So I would never say that chocolate pudding causes my headaches to go away. I would say every time I eat chocolate pudding, I no longer have a headache. And here's the math that shows that. But there may be another parameter that has an impact. And so we never want to, when you say this causes this, you're limiting all the other options. And since statistics is used a lot in business models and in science for sure, we never want to say one thing causes the other, because there might be another parameter that we're not thinking of that actually causes something. So anyway, straightening scatter plots. Straight line relationships are the ones that we can measure with correlation. When a scatter plot shows a bent form, it's consistently increasing or decreasing. We can often straighten the form of the plot by re-expressing one or both variables. We'll talk about that in chapter 9. There are such things as, there's a couple ways to approach that. You could do regressions, you could do linear regressions, you could do exponential regressions, you could do the log of the data, which tends to straighten out the data. That's chapter 9 stuff. Don't say correlation when you mean association. Right? We have to be very, and this is where they'll trip you up on the AP exam. They're going to show you some data and say, does this cause this? If you say yes, it's wrong. If they say, is there an association, then that's different. That's a different meaning. The word correlation is reserved for measuring the strength and direction of a relationship between two quantitative variables. More often, though, people say correlation when they mean association. Right? Correlation is a number where we actually measure it. The correlation coefficient measures how tight of a fit the data is to the linear model. Don't correlate categorical values. Make sure everything is quantitative, measurable. Don't confuse correlation with causation. Scatterplots and correlations never demonstrate causation. There's too much stuff in the big world to determine what causes what. These statistical tools can only demonstrate an association between two variables. Chocolate pudding may cure my headaches, but maybe I'm starving and I eat a little chocolate pudding and my headache goes away. Okay? If I were to try and do a linear association with this particular graph, the numbers would be goofy. No matter where if I draw a straight line through here, if I draw a straight line through here or here, it's not a straight line. So be sure that it's linear when you try to apply these methods. If it doesn't look like a straight line, you say, well, this looks like a straight line, and this looks like a straight line. No, all the data has to be straight. Although you could make a prediction doing this and doing this, but we're not going to do that in this chapter. Here's a correlation that has a coefficient of 0.979, but the relationship is actually bent. In other words, you could draw a straight line through the middle of this, and the dots, the plotted points, are going to be fairly close to the line. But if you look at it, it's slightly bent. I could probably get a more accurate correlation coefficient if I used a different model other than a linear. So you can also look at that too. This outlier way over here will change all the math. Okay. Now, with outliers, you can leave them in, you can take them out, but you got to be careful. You can't just toss them out and not tell people. You got to do the math on everything and let people make the determination on that. That's a heck of a shoe size too. Look at that. So this is the person's IQ based on their shoe size, and you see everybody's all clumped up between 100 and 25. That's why I always tell you guys we're all about the same average intelligence, right? Well, I don't know who this person is, but there's something wrong. They've got the biggest feet I've ever seen, and they're a genius. Okay. There might have been something wrong there. Maybe they filled out the survey wrong. Maybe they misunderstood it. Maybe they are an anomaly. Maybe they are a giant and extremely gifted. All right, here's some tips for your AP class. Just like the rest of the graphs in this course, scales and labels are required for full credit. So if you go to a graph of scatter plot, you got to label things, okay, to get full credit. If you don't have a star, either axis at 0. If you don't have to, start either axis at 0. But once you start scaling the axis, it should keep the same scale throughout the entire length. So we'll talk about that. I'll show you that and maybe some of the homework problems. You don't have to start at 0, 0. You can skip some parts, but when you start scaling things, that scale needs to be consistent. Describe a scatter plot. Describing a scatter plot should be done in context and include the form, strength, and association. There is a strong positive linear relationship between age and height. Okay. We usually refer to R as a simple correlation, but the AP test usually refers to R as the correlation coefficient. Don't get confused by the additional word coefficient. It's just R. It's a coefficient because it's a scalar multiplier, or can be, to the value itself, right? It can be used mathematically. So if I work at a retail store and that retail store sells pants, I need to know how many sizes of each. I need to know how many pairs of pants of each size I need to order. There's a lot of math involved in that. If I'm selling hoodies, right? When I went to Walmart to buy a hoodie for the school, they had 2 of my size. They didn't have 10 of my size. They had 2 of my size. They had a bunch of other sizes too. How they determine how many of each size they need is based on how many sizes of hoodies they sell. There is a correlation and an equation, and they make a prediction. If I'm going to sell a new hoodie, I need to have this many in this size, this many in this size. The correlation coefficient, if it's closer to 1 or negative 1, that helps to determine how accurate their predictions will be. Okay? And that is it.